It's my pleasure to introduce Annalisa Iuorio today. Annalisa completed her studies at the University of Naples, Federico II, and obtained her PhD at the Vienna University of Technology under the supervision of Peter Smoljan. And then she worked at RICAM in Vienna in the group led by Marie-Therese Wolfram, focusing on pedestrian dynamics. And currently she's working at the University of Vienna as a principal investigator of the FWF Finberg program, mathematical models to study toxicity effects on vegetation. But today she's going to talk about a PDE model for unidirectional flows, stationary profiles, and asymptotic behavior. Please, Annalisa.
Thank you, Cinzia, for the introduction. Thank you to both Andrea and Cinzia for organizing this seminar and giving me the possibility to present my work. So I am sharing the screen. I hope you see it.
Yes, fine.
Okay, great. Yes, so as Cinzia mentioned, what I'm going to talk about today is actually, let's say, the first paper that I did with during my time in RICAM in the group of Marie-Therese Wolfram, and is a joint work with also Kaspar Jankowiak and Peter Smoljan. And it deals with the analysis of stationary profiles and asymptotic behavior for a PDE model arising in the context of pedestrian dynamics, in particular when focusing on unidirectional flows. So the outline of my talk is the following. I'm first going to introduce the model, explaining why are we interested in studying this specific scenario and how we derive the PDE model that we further investigate. And then I'm going to move to the main part of the talk where we basically, let's say, put this PDE model into, or the steady state equations corresponding to the PDE model under study into a dynamical systems framework in order to apply specific techniques, in particular geometric singular perturbation theory, to construct singular solutions and derive results on the full problem as well. I'm going to conclude the talk by briefly showing some numerical experiments that we performed, both comparing our 1D reduction with the full 2D simulation of the model, and also concerning comparison of the numerical profiles for the full model with the singular ones that we obtained analytically. So the scenario that we're going to focus on is, as I mentioned in the beginning, unidirectional flows. So what we are ideally thinking of is a flow of a pedestrian crowd in domains which have a single entrance and exit. The simplest example can be a corridor, but we are also going to consider further types of geometries. But the most important thing is that we have a single entrance and exit. And it has been observed both experimentally and numerically that considering different inflow and outflow conditions, as well as considering different shapes for the geometry of the domain, can influence the behavior of the solutions, particularly of the steady states, and can also lead to the formation of boundary layers. And this, of course, in practical terms means that the pedestrian crowd, let's say the density of pedestrians increases in proximity of a very small spatial location, which is, of course, something that one would like to avoid, especially in, let's say, in the organization, for example, when large crowds are moving. So our main goal was actually twofold in some sense. The first goal we had was to identify regions in the parameter space given by the boundary conditions, so the parameters that we will see will enter in the boundary conditions, in which stationary solutions share some similar features or have the same structure essentially. And to do this, we actually apply techniques from geometric singular perturbation theory, or GSPT, and also investigate how the bifurcation diagram, the structure of the bifurcation diagram, depends on the geometry of the domain, and in particularly how one can then move from one region to the other. So the starting point of our investigation is actually a model introduced by Burger and Pichman in 2016, again in the context of a transport model for a crowd of pedestrians. And in this model, in this PDE model, we see the dynamics of the variable rho, which represents the density of the pedestrian crowd, subject to a total flux, which is represented by the equation for J that we see here. Here we also see the dependence of the equation on this vector field U, which is a normalized vector field defining the direction of motion. And the choice for this specific vector field also plays a role, of course, in the description of the two-dimensional model. And as we're going to see later on in the numerical part, we consider different possibilities for this type of vector field. The two most interesting things, especially for me and Peter, coming from the dynamical systems perspective, more or less, are the following. The first one is that the diffusion coefficient is represented here by this small parameter epsilon. And the second one is that the boundary conditions, which are represented here, are non-standard in the sense that they depend strongly on the variable rho, so on the density of the crowd. The first row essentially tells you that, let's say, the crowd doesn't move through the ceiling or the floor in short terms. And this second line tells you that how or at which rate the pedestrians enter through the entrance. So it has a sort of carry capacity effect in the sense that when rho reaches or is close to its maximum value, which is 1, it is assumed with this boundary condition that no pedestrians enter in the domain, or very few. And the last condition is the condition on the exit, so through sigma, where the crowd leaves the domain with an outflow rate beta. So the main or the first step that we considered in our investigation to be able to carry a more rigorous or a more detailed analysis on this problem was to consider a 1D reduction of this 2D model by averaging on cross sections. So if you consider, let's say this is a sketch of a generic domain that we might consider, which is symmetric with respect to the horizontal axis, what we do is essentially average on cross sections. W is now the function that defines the profile of the geometry. And what we're essentially able to do is to subsequently perform this 1D reduction by further assuming that the density of the crowd, or the main effect that density plays in some sense, depends only on the X direction more than on the Y direction. This is a reasonable assumption in the context of narrow corridors. Of course, if one considers more complex geometries, one should also carefully take this step into account. But for the kind of geometries that we were interested in, it was a feasible assumption. And what we are interested in, or our main focus of our investigation, is stationary states for the 1D reduction of this PDE model. And this essentially reduces to the equation that you see in the yellow box at the bottom, where now we have this function K, which essentially, let's say, entails the features of the geometry of the domain. And now the boundary conditions are given not at, let's say, the entrance at the exit, in this case, in this 1D reduction, correspond to the points 0 and L, respectively. So in order to investigate this model, as I said, let's say, then the first step in our investigation was to convert this model, this PDE model, into a, let's say, dynamical systems framework, since the presence of this small diffusion coefficient and also some preliminary numerical experiments revealed that this model, let's say, intrinsically has a multi-scale structure. So we can, in spatial terms, let's say, divide the dynamics into, let's say, what happens on a small scale and what happens on a large scale. And this recalls basically the idea behind so-called fast-slow systems, where the idea is exactly the same, only in terms of, let's say, time as the main variable rather than space. But in order to, let's say, give a more clear overview on what we are going to do next, I'm going to spend a couple of words about fast-slow systems in a more general framework. So, as I said, in this case, in the general introduction, you talk about fast and slow because the main independent variable is thought as time. In our case, it will be space, but it's exactly the same. So fast, slow systems are systems where, let's say, we can decouple or we can divide the dynamics of certain variables and certain other variables due to the presence of a small diffusion or a small coefficient, sorry, epsilon. Because as we can see here, the dynamics of the variables x have, let's say, go as 1 over epsilon. And when epsilon is small, this means that the dynamics of the variables x are much faster than the dynamics of y. And that's why the variables x are called fast and the variables y are called slow. And they are particularly, let's say, interesting to study because of this intrinsic multi-scale structure, but also because there are, let's say, powerful techniques, in particular geometric singular perturbation theory, that allow to study these kind of systems in a rigorous and also constructive way. So one can, by rescaling the independent variable, so in this case time, via this parameter epsilon, one can obtain an equivalent reformulation of the above system, which is written in this case in the slow scale, in a fast scale. These two systems are perfectly equivalent. But let's say, so one might ask, why should one bother to do this? The reason is because when considering the singular limit epsilon 0 in the slow and the fast scale separately, one obtains two easier sub-problems to deal with, and then one can say something about the structure of the full problem. So when one considers the singular limit epsilon 0 in the slow scale, one obtains the so-called reduced problem, which gives you the dynamics of the slow variables y on what is called the critical manifold, which is defined by the algebraic equation that you see here. On the other hand, when you consider the limit epsilon 0 in the fast scale, so in the problem here at the bottom, you obtain what is called the layer problem, which gives you the dynamics of the fast variables x on layers, because one thinks of the variables y as, let's say, fixed layers or layers where the value of y is fixed. So the idea is that these two sub-problems are simpler to analyze, and under suitable assumption, one is able to construct singular orbits in the singular limit epsilon 0 by matching pieces that come from the reduced flow and the fast flow to obtain the skeleton, so to say, of what is the solution to the full problem. And under, again, suitable assumptions, one can then infer, let's say, not just existence, but also information about the structure of the solutions to the full problem. So when one considers epsilon as positive but small. So we basically plan to adopt this kind of strategy also in this context, or in the context of our pedestrian model. And to do this, we focus on, without loss of generality, on a specific domain, which is the so-called case of the closing channel. And the closing channel is essentially represented by a positive function k with decreasing, which is decreasing, so with negative derivative. And therefore, when we introduce this function g, which is given by the ratio between the derivative of k with respect to x and the function k, this is also a negative function. And again, without loss of generality, we assume that the length of our domain is equal to 1. And we also introduce, let's say, the spatial variable x as an extra dynamic variable in our system. And it will become clearer later on why we choose to do this. So using, let's say, following these assumptions and also introducing this third variable in the system, we can rewrite our our steady state system in the following way. So again, on the left, you see the slow formulation, where again, you see the small parameter epsilon appearing here on the left-hand side. And so analogously to what we've shown in the general case, by rescaling the spatial variable with the small parameter epsilon, we can obtain the equivalent fast formulation for our system. So it's now a system with respect to the variables j, c, and rho, which is the density. And the boundary conditions actually are not affected by this procedure. They stay exactly as they are, but one can already maybe hint at why it was, let's say, useful to introduce the spatial variable as a dynamic variable in the system. And that's because now, let's say, the boundary conditions for our problem, when we are going to think about them in this, let's say, dynamical systems geometric framework, are going to correspond to manifolds that we just have to match. So we follow essentially the same approach that, that we have illustrated in the general case. So we first look at the singular limit epsilon 0, both in the slow scale and in the fast scale. In the slow scale, this leads to the reduced problem, which is fairly simple, given by just these two equations, on the critical manifold, which is defined via this algebraic constraint in our case. And it turns out that it's actually more convenient to study the reduced problem in terms of the variables rho and psi rather than j and psi. And this is possible because j and rho are, let's say, related to each other via the constraints, which is given by the critical manifold. So by just, let's say, plugging in this constraint in the equations and rearranging terms in a convenient way, we can rewrite the reduced problem in the following form. And this plot that you see here below is essentially the projection of the dynamics, the slow dynamics, on the critical manifold in the two-dimensional space psi and rho. And again, this is, of course, what we observe in the specific case of a closing channel. We would observe slightly different dynamics if we consider different geometries, but the analysis that we're going to carry out is specifically thought for this case. So all the plots that you're going to see are referring to this specific case. Then we can obtain the layer problem by setting epsilon equal to 0 in the fast formulation of our problem. So as you can see, it's a fairly simple problem. We're just left with the equation for the rho variable, for the density, and on, in this case, layers of fixed j and c. And it was actually already visible here. Basically, okay, so the critical manifold now in the projection on the j rho plane, so for a fixed value of j, of x, of c, sorry, the critical manifold reduces to the union of these two curves, the upper part, which is attractive, and the lower part, which is repelling, with respect to the fast flow, which is here depicted in green. And these two branches meet at here, it just looks as a point because we are just considering a slice for a fixed value of c, but it actually corresponds to an entire line when one considers the full three-dimensional space j, xi, rho. And it's a line of fold points, which will also play a role in our analysis, as we will see later on. So the idea is now to match this information, what comes from the reduced problem and the layer problem, to construct what should be a singular solution. And in order to do this, this is, let's say, you're going to see these plots later on as well. So let's say, don't be afraid if you don't get all of them at the same time. But it's just to illustrate what we're going to do, basically, which kind of strategy we're going to use. So using this dynamical systems approach, what we are basically doing is transforming these boundary conditions into manifolds. These two manifolds, actually, the manifold at the left will always be indicated in orange, and the manifold at the right will always be indicated in purple. So what we're basically always going to do, is to consider a manifold of boundary conditions at the left as a set of points where we are allowed to start our, let's say, evolution. Then we're going to use the fast flow to, let's say, put ourselves on the critical manifold, because it's only on the critical manifold that we are then allowed to move from 0 to 1 using the slow flow. That's something that's basically what you see here sketched. And then once we are arrived at the end of our domain, so at c equal 1, we need to match our evolved solution with the manifold of right boundary conditions, which is the one at the right. So as a sketch, this is basically what we are going to do and what is going to give us the profile of the singular solutions. Here you see one example, but for different regions, we will have, of course, a different sketch of a singular solution. And this is its depiction in 2D, so just with respect to psi and rho. And this would be the depiction of this singular solution in the full three-dimensional space. So when one considers also the J variable here. Okay. So basically, in a bit more details, what does it mean to reinterpret these boundary conditions as manifolds in this three-dimensional space? We recall that basically we start focusing on the boundaries that are at the left of our domain, so at the entrance. There we had that J had to be equal to alpha times 1 minus rho at C equals 0. So that means that if I consider a slice in my three-dimensional space at C equals 0, so I have something in J and rho, I have that there has to be a relation between J and rho according to the boundary conditions. And this is basically represented by the whole line that you see here. Maybe I'm also going to make it bigger. The whole line here. So in principle, all these points on this line are good points to start my orbit because they all satisfy the boundary condition at the entrance. However, since I have to match these points with the boundary conditions at the right, I cannot consider the points which lie on the gray area of this line, because if I would start from here, the fast flow would immediately bring me away from the critical manifold, and therefore there would be no chance for me to use the slow flow and reach the other side, so to say. So I exclude the gray area, and the only good points that I can consider are the ones in the orange part. Now, let's say of these points, there is actually a very lucky one, a very special one, so to say, which is the point where this line intersects the critical manifold. At that point, I basically don't need to do anything. I'm already on the critical manifold. I can already start with the slow flow and go to the other side, so to C equal 1. However, if I am on any other point on the orange line, which is not this point, which we actually are going to call small l, I still can go on the other side by first using the fast flow to go upwards and reach the critical manifold. So all these points are also good points because through the fast flow, through the green lines which are shaded here, I can go up until I don't meet the critical manifold. And then from there, I can start my slow flow and reach psi equal 1. So the only difference in this case, of course, this manifold depends on alpha. But alpha actually only regulates the slope of this line. So when alpha is less than 1/2, you always have this, let's say, splitting between this small point L and this upper orange part, which is the projection of the manifold of boundary conditions on the critical manifold. But if alpha is greater or equal than 1/2, actually, you have that this point is already lying in this upper part. So there is actually no distinction between these two objects. So basically for the right-hand side, for the right boundary conditions, we have to do exactly the same thing. We proceed in a very analogous manner. We define the manifold of right boundary conditions here as the purple line. Again, the gray area is not feasible because nothing on the slow flow would ever bring me there. So I can only consider the points, the purple points here. And again, we have a special point, which we call small r, which is the point where the manifold of right boundary conditions intersects the critical manifold. That means that basically through the slow flow, I managed to arrive exactly where I was supposed to arrive. I don't need to do anything else. But all these other points are actually also good points, because I can also reach them if through the evolution of my manifold of boundary conditions at the entrance via the critical manifold, if I ended up somewhere down here, I can still exploit the fast flow to move up and reach these points, so reach the manifold of right boundary conditions. And again, we just need to distinguish, let's say, the case between beta less than 1/2, where these two sets are splitted, from the case where beta is greater or equal than 1/2, where they are actually on the same side. And now, essentially, the idea is to, okay, once we have these two manifolds of boundary conditions at the entrance and at the exit, we have to match them through the slow flow. So what we actually do is we start from the manifold of boundary conditions at the entrance, and we let it evolve until C equal 1. Then we check the intersection of these evolved manifold of left boundary conditions up to C equal 1 with the manifold of boundary conditions at the exit. And if this intersection is non-empty, and in particular returns a unique point, then we have our unique singular solution for our boundary value problem. So all these objects that you see are just the definition of the evolution of, let's say, the single point and the, so to say, big orange part on the critical manifold once you have let it evolve up to C equal 1. It turns out actually that for our analysis, it is very useful to identify or to work with some special orbits. Actually, in total, they are 6, but actually they are 3 plus their reflection with respect to rho equal 1/2. So the first special orbit that we consider is what we call S1. This is defined as, with respect to the reduced flow, is defined as the orbit such that ends basically at the fault point when C is equal to 1. So it's the green, sort of more or less greenish orbit here in the plot here. So since we have explicit formulas for the flow, both the reduced and the fast flow actually, once we impose this constraint, we can uniquely define the value rho f, so the value of the density at C equals 0, which satisfies then the constraint that rho has to be equal to 1/2 at C equal 1. So it has to end at the fault point. And we fix this value to be less than 1/2, just for sake of sort of clarity, but and let's say to make our investigation rigorous, but it is up to, let's say, it was our choice to do so. The second special orbit that we consider is what we call S2, and is here depicted in magenta, is essentially the orbit which tells us we are starting already at the right point. We are starting from the point small l, basically. And starting from the point small l basically means that the density at C equals 0 is equal to alpha. So we are already on the critical manifold. And again, we have explicit expressions for the slow flow. So we can also uniquely define the value of the density rho at C equal 1. And we define it as rho star alpha. It's important to notice that this orbit is well defined only when alpha is less than rho f, because if alpha is greater than rho f, the slow flow would bring us directly on the line of fault points, and we would not be able to arrive to C equal 1, which is the point where we have to meet the right boundary conditions. So we always have to consider alpha less than rho f for this special orbit S2. And finally, the last orbit S3 is essentially the orbit where I end at the right point. So I am basically reaching already the right boundary condition, 1 minus beta at C equal to 1. And therefore, I can also trace back the corresponding value of the density rho, which satisfies this constraint. And we call this rho star beta. Again, we have, and as let's say the other three orbits, which we call S tilde I, are just the reflection of these orbits with respect to rho equal 1/2. It is interesting to see that these quantities, so this rho f, rho star alpha, and rho star beta, we can define them via, depending on the function k under consideration, but they depend on the value of this function. Okay, so now that we have
Annalisa,
sort of,
sorry,
see,
so
yeah.
we missed the last part because your internet connection.
Sorry,
Mine, I don't know.
I didn't realize. Okay, which part? From which part?
Well, just near really the end of the slide.
Yeah.
Okay, so let's say the last thing I said was that we can calculate these quantities, so the rho f, rho star alpha, and rho star beta, and they depend, of course, on the function k, but it was quite interesting to observe that they depend on the function k only through its values at the boundary, so at 0 and 1. And of course, they depend on the parameters alpha and beta, so the inflow and outflow rates. So once we have now identified these sort of main solutions in our analysis, we can then proceed to one of our main goals, which was to divide the bifurcation diagram with respect to the parameters alpha and beta into regions where singular solutions essentially share the same features, the same structure. In particular, for the closing channel case, we identify 6 regions, and in each region GI, we say that the singular solution is of type I, of course, for I that goes from 1 to 6. And in such bifurcation diagram, we also identify certain curves that separate the relative regions. And these curves are actually sort of naturally arising from our analysis because they are defined essentially as the curves along which some of the special solutions that we have illustrated in the previous slide coincide. So this is essentially of how the singular bifurcation diagram looks like, and how the corresponding singular solution, the prototypical singular solution, looks like in every region. And so and the gray line represents the level rho equal 1/2, so sort of in the middle. The blue parts represent the parts of the singular solutions which come from the slow flow, so the reduced flow, and the green parts, which are essentially the fast jumps, so the boundary layers, are corresponding to the parts where we have a contribution from the fast flow. And actually the transition between almost all regions is fairly smooth. For example, if you see when you go from region G4 to G6, actually the only thing, basically what happens at on the line gamma 4, 6 is that you have an orbit where the slow flow ends precisely at the fold and you have no fast jump on the right. So it's a fairly smooth transition between these two regions. But there are 2 special cases, gamma 1,5 and gamma 2,3, where actually the change in the solution is quite dramatic, and therefore our analysis does not cover these specific cases. And we're also going to see in a minute why it is so. So our main result for the singular case is actually the following. It essentially tells us that we have shown a lot of plots for the closing channel case, but actually in the proposition, the singular limit result applies for any k which is just monotone decreasing. Then basically, this tells us that whenever we pick a value of alpha and beta in a specific region GI, there exists a unique solution gamma I of type I. And this solution is essentially obtained by matching pieces coming from the layer problem and the reduced problem. And the sketch of the proof, I'm basically just going to show drawings at this point, but the proof is essentially based on the shooting strategy that I have outlined before. But it is kind of interesting here to see why we get 6 regions in the bifurcation diagram, because actually the way we construct our solutions, which was to, let's say, check the intersection between the evolved manifold of boundary conditions from the entrance and the boundary conditions at the exit, this intersection can only happen in three ways. Either in the first case, we have that the point L, little l, evolved up to c equal 1, intersects, let's say, the big purple piece on the right-hand side. Or on the other hand, the big orange piece on the critical manifold on the left intersects the small point r on the right-hand side. Or the case which we actually analyze in the middle is the case where the big orange piece on the critical manifold on the left and evolved up to c equal 1 intersects the big purple piece on the right, so it's c equal 1. So we're first going to, and for each one of these three scenarios, we are basically going to obtain two singular solutions. So the first scenario is the one that gives us orbits of type 1 and type 2. As I said, in this case, we are already starting from the right point. That means we don't have a boundary layer at the left because we are already at the critical manifold. So we start from already at this point here, where the manifold of left boundary conditions intersects the critical manifold. Then we just have to follow the slow flow. And then we use the fast flow to meet the manifold of right boundary conditions. So we have a boundary layer at the right, and our singular solution essentially looks like this. Type 2 is not very different in the sense that we again start from the special point. So we have no layer at the left. We follow the slow flow up to c equal 1. But now the layer that we have at the right is such that the row along the layer decreases. So we have a fast flow pointing downwards. And this is why we get a singular profile of this type. In the second case, in the second case, instead, since we are considering the case where the big orange piece intersects the big purple piece, that means that we are not starting from the special point and we are not ending at the special point. So we will have boundary layers both at the left and at the right. And again, we have two types which are, let's say, different only from the fact that in the type 3, we have a boundary layer on the left where row increases. Then we follow the slow flow. And actually, both for type 3 and 4, we are in this special case where we end precisely at the fold. But at the fold, once we are there, we are allowed to meet the right boundary conditions by following the fast flow downwards. So we obtain an orbit which looks like this. And the type 4 is actually not much different, is only different from the fact that, and here actually we had to enlarge the picture a little bit because it was fairly hard to see. But the only difference is that the boundary layer at the left is also such that row decreases along the fast flow. But we still have a slow flow that ends at the fold. And from there, we can jump down to meet the manifold of right boundary conditions again. So we have a solution which looks like this. And finally, the third case is the case where we are ending at the right point. So we have no layer at the right, we only have it at the left. And therefore, we just distinguish two scenarios. One where, maybe I will directly show this. So one where we have a boundary layer where row increases at the left. And the type 6 is, again, the dynamics are fairly hard to see. So we had to consider also a zoomed version. But we have here a boundary layer where row decreases. That's the main difference between the two. And again, the excluded cases from our analysis are the, let's say, the values of alpha and beta, which lie on the separating curves gamma 1,5 and gamma 2,3, where we saw that actually the two corresponding regions had very different behavior. And that's actually why, because the possible slow transitions from c equals 0 to c equal 1 are not uniquely determined, but there are two which are both equivalently valid. And therefore, we end up with a continuum of singular solutions because we can jump at, using the fast flow, we can jump at any c between 0 and 1 from the lower branch to the upper branch. So this leads to a loss of uniqueness, and therefore transversality arguments that would be able to give us persistence of solutions do not apply here. Okay, so now that we have our skeleton or our full singular solution in the case epsilon 0, we can now say something about the solution to the full problem where epsilon is positive but small. And in this case, actually, we have that whenever we take alpha and beta in one of the regions in the bifurcation diagram, our boundary value problem is a unique solution, rho, which depends, of course, on both alpha, beta, and epsilon. And in the phase space formulation, this solution actually corresponds to an orbit, which we call gamma I epsilon, which is close to the corresponding singular counterpart. But the order, let's say, regulating this closeness is slightly different for the case, let's say, of type 1, 2, 5, and 6. This is just order epsilon. It's the simplest case. But for type 3 and 4, the fact that the slow flow ends at the fault point implies that the coefficient of the power or the epsilon here is equal to 2/3. And again, here I'm also just going to sketch our strategy, but essentially we use a similar sort of approach than what we did in the singular case, because we consider these three main cases. And actually the case 1 and case 3 are sort of one the reflection of the other in some sense. So case 1 is when alpha and beta are in regions G1 and G2. In this case, actually, we can use Fenchel theory to infer that basically our manifold of left boundary conditions will still intersect the perturbation of the critical manifold in a point which we'll now call L epsilon. And we have that only points on this manifold of boundary conditions exponentially close to this point will stay in a neighborhood of the corresponding singular solutions all the way up to C equal 1. Then once we're there, we can denote these points, this set of points by L1 epsilon, and we will still have the intersection of this manifold with the manifold of right boundary conditions, which we now call P1 epsilon. So the full orbit is then obtained by considering the, let's say, the trajectory backwards from this point P1 epsilon up to C equals 0. In the second case, this is the, let's say, more delicate case because we have this passage close to the fault point rho equal 1/2. So here, what we actually do is we take our manifold of left boundary conditions L, we consider an extension of a small segment containing P0, which is the initial point for the singular orbit, and we let this small segment flow under the action of let's say the full flow of the system in that case up to C equal 1. And the manifold that we obtain is a smooth two-dimensional manifold, which we call M epsilon, and is basically the manifold depicted in red in the plot here. We have that actually parts of this manifold M epsilon are close to the point P1, which is the original endpoint of the singular orbit. And they will be ordered epsilon to the power 2/3 close to the saddle line in a neighborhood of P1. So this guarantees that actually this manifold will still intersect the manifold of right boundary conditions at a point which we call P1 epsilon. And then we used exactly the same strategy. We track the entire orbit backwards up to C equals 0. The third case is exactly analogous to one upon reversal of the flow direction. So the last thing that I want to show you is the numerical, let's say, numerical experiments that we performed. The first is basically a comparison with the 2D simulation, so the Y average of the 2D model, considering actually two vector fields for the direction of motion. One is the so-called, what we call UE, which is the gradient of a function phi, which solves the Eikonal equation. And the other one, UL, is the normalized gradient of the function psi, which solves the Laplace equation. these are, let's say, two equivalently valid, choices which are used in these kind of models in the literature. But it turns out that, let's say, in most cases, the Laplace choice is the best ones because it is also able to deal better with sharp corners. For example, what we have here in the scenarios C and D, which correspond to here, this is basically a piecewise constant corridor, and this is like a bottleneck scenario. This is a closing channel, so it's basically what we have used in our analysis so far, and this is a straight corridor where actually there is no distinction between the 1D reduction and the 2D model. They perfectly coincide as expected. And the last thing is that when we try to reproduce the bifurcation diagram numerically, considering a small value of epsilon, but still positive, we obtain perfect agreement with what we obtained analytically in the singular limit. So we have that the solutions correspond to a perturbation of the singular solutions that we had obtained in the singular limit epsilon 0. We were also able to verify this on, let's say, the curves dividing the regions, which were easy in some sense, but even the numerics is very tricky at the, let's say, curves where our analysis does not hold. So to conclude, using dynamical systems techniques, in particular GSBT, we were able to analyze stationary states for a PDE model with non-standard boundary conditions, where the inflow and outflow rates depend on the density of the pedestrian crowd, and also to identify the main feature with respect to the system's parameters. Such analysis was, let's say, also confirmed and validated by the numerical experiments that we conducted. Of course, there is still plenty to do, and what we are actually already starting to do is to consider more general geometries and domains, where actually also we have started observing numerically interior layers can also arise, and also consider further approaches for the 2D approximation, which can also improve the, let's say, accuracy of our 1D reduction with respect to the 2D simulation. You will find more details in the preprint. It should be out soon also on Journal of Mathematical Analysis and Applications, but in the meanwhile, you can find it there. And I would like to maybe take this last minute to advertise a research school that I'm organizing with Cinzia, one of the organizers of this seminar in Bonn at the beginning of April, which deals with diffusive systems, pattern formation, bifurcations, and biological applications. If you can find more information on the dedicated webpage, or if you're interested, ask me or Cinzia more information about that. And without further ado, I would like to thank you for your attention.
Thank you, Annalisa. Thank you for your interesting seminar. And other questions, comments? So you can either raise your hand or just, yeah, Andrea.
Well, just a sort of a naive question, if I understood, to understand better the model. The idea is that you have that the flux is due to a small diffusion plus some, let's say, directional force that you, in the application, you try that was the solution of the Laplace equation, or did I got it wrong?
Yeah, so let me go back to the original. Okay, so in the original system, you have that the flux is regulated by this vector field U, and this vector field is essentially, let's say, assigned as a choice from the modeler, depending on, let's say, could be experimental data, could be, let's say, what seems to be the most reasonable approach or the most reasonable behavior observed in experiments. And two of the main options which are used in the literature are these ones. So this, let's say, gradient of the solution to the Iconal equation and the gradient of the solution to the Laplace equation. And maybe I can actually even, let me see. Although this is, I hope that now I can, okay. So this is the case of a bottleneck. So it's already a little bit different from the geometry that we have considered, but essentially, this is, for example, where we started to examine the different behavior of the solutions when we considered the Laplace or the Iconal case for the U. And the arrows just give you the direction of motion. So in principle, let me see if I can start it. Okay, so the arrows should indicate you the direction of motion, and in blue, you see how the density is changing. But let's say the difference, the main difference between the Laplace and the Iconal is that the Laplace is sort of better able to deal with corners, because once, let's say, you hit a corner, then you change your direction and you go like this. But in the Iconal case, let me see if I have it. Yeah, so unless you are, let's say, already here on the sloped part, when you, let's say, approach corners, you reach this like high concentration, high density, which is also, let's say, a bit less feasible from, let's say, an applied perspective. So that's actually also why we were considering we were more focusing on the Laplace choice, but actually now when, let's say, we are also considering further experiments where we also have that the vector field is not uniform in the entire domain, but let's say changes depending on whether you are, let's say, at the entrance or at the exit. Let me see if I have here, for example. So this is, for example, a mixture of, let's say, Laplace and Iconal, which we have defined probably better here, I think. Yeah. So this is the case where one considers the Laplace field on the left, but the Iconal on the right. And this is very hard to see, but the arrows kind of indicate how the direction of motion is assumed to be. So it's a modeling choice in principle.
Okay. Thank you.
Any other questions for Annalisa? I have one, Annalisa. So Fasma? Yes, please. We cannot hear you.
You cannot hear
Yeah,
me?
no, okay.
Just curiosity, what are the numerical scheme that you used for solving, for obtaining numerical results? And what kind of problems have you faced in the application of the schemes? Thank you.
Thank you for your question. So I have it right here because I was not the one mainly responsible for the numerics, but I thought this would be a question that could come up. So essentially, what was used was the Newton's method, and in principle, let's say, apparently, at least, let's say, especially for the geometries that we have adopted, it was, let's say, sufficient to, let's say, to use this. I think it was a finite element library, which is called Phoenix. And this was, let's say, in the cases, in the geometries that we have analyzed, fairly good to perform this. In the cases where, let's say, so the only cases or the main cases where we encountered some difficulties were the ones where, so along these separating curves, which I was mentioning before, so these critical ones where we have this abrupt change between in the structure of the singular solution. But in that case, let's say the scheme is extremely sensitive to parameter changes. So it's this was also somehow an indication for us that let's say a confirmation of what we expected analytically, that if we take alpha and beta along that line, it is let's say not straightforward to obtain a well-defined unique solution. I hope this answers your question. Thank you.
Any other questions? So just one from me, Annalisa. So
yeah.
I'm curious to know if there is an interpretation about of the bifurcation diagram with respect to the meaning of the parameter alpha and beta. So,
yeah, so it's a very interesting question. Yes. So essentially, let me see if I can find it now. Here. Okay. So
and I don't remember the meaning of alpha and beta. So if you can.
It's true. So essentially, alpha is the parameter regulating the inflow rate. So how fast the pedestrians enter the domain. And beta is the one that regulates the outflow. So how fast they leave, essentially. And the idea is that, let's say, the boundary layers are the points where you have this high density of pedestrians. And in principle, let's say it is expected, for example, that when alpha is very low, so that means that they enter, let's say, at how to say, a fairly slow rate. There is, so to say, no problem here at the entrance, but depending on, let's say, on beta, there could be this concentration at the exit. Whether, let's say, the density increases or decreases, then, let's say, strongly depends on the structure of the on the region that one is considering. If I let's say recall correctly, you have let's say different scenarios depending on whether, let's say, the inflow rate is larger than the outflow rate. So if alpha is greater than beta, you can have high density regimes, but and especially let's say in the case alpha greater than beta, you can have then let's say a fast drop, sorry, you can have this sharp increase close to the entrance. So in principle, it strongly depends on how alpha and beta are related, and if one is greater than the other, you may have the location of these boundary layers at the entrance or at the exit, more or less.
Okay, thanks. Any other questions? So I don't see questions in the chat or raised hands. So we can thank Annalisa again for the interesting seminar.
Thank you.
And the next one is on the 27th, right?
Sì, giovedì 27.
Okay, at 3 p.m. So thank you all.
Grazie a tutti, grazie.
Thank you. Bye.